Hey guys, thanks for watching. This is Late Night with Dr. Neutron. I'll be doing problem 13 and talking through the whole thing, so if you were working on homework, please watch this video. If you haven't started on the homework, now is a good time. So this is problem 13. Let's take a look at problem number 13. Okay, so in the figure, particle 1 of charge Q1 equals 0.96 microcoulombs, and particle 2, charge Q2, are minus 3.02 microcoulombs, are held at a separation L of 9.3 centimeters on the x-axis. If particle 3 of unknown charge Q3 is to be located such that the net electrostatic force on it from particle 1 and 2 is 0, what must be the x coordinate and the y coordinates on particle 3? Okay, so even though there's a drawing there, I'm going to draw the picture, because when you do physics problems, you should always draw the picture. I cannot emphasize that enough. Sometimes you get insights from the picture. Okay, so this is L, and we've got Q1 here. This is 0.96 microcoulombs, and this one is minus 3.02 microcoulombs. Okay, so this can be a little confusing because we don't know what the charge of that third particle is, but it doesn't actually matter. We don't even need to know it in order to solve this problem. Okay, so the way that we will do it is there are three different regions. We could say, okay, what if I put my charge here in between? Okay, well, if I put my charge in between there, it will be either, so we'll say this is negative or positive. If it was in between, it would be attracted to one of these. So if it was positive, it would be pulled that way, and if it was negative, it would be pulled that way. Okay, so it really can't be over here. Okay, so it can't be in the middle because there's just no way that we can imagine that it would be true. Now, if we bring the particle outside of the y-axis, it's going to be repulsed by one. So if we say bring it up here, let's bring it way up here. Okay, it would be repulsed by one and attracted to the other. So if it was negative, it would go over here, and if it was positive, it would go over here. So that means that y must equal 0. I can't think of a place where we could stick another charge where it would not move. Okay, now we have to look at the two charges here. So this charge is very big. Okay, and the way that electrical charges work is that they can block each other. So if we have a positive over here, but a really big negative charge over here, if we put a negative charge over here, it would only see this charge over here. This would basically block it. If we put a positive charge over here, this charge would block it, and it would be pulled in this way. So really, we can't put anything over here. We can't put anything up in the middle or off of the y-axis. So the only region that it can be in for this particular setup is over here. If the charges were equal and the same sign, we could maybe put it something in the middle, but they're not. Okay, so this has to be this one's much smaller than this charge over here. Okay, so it has to be something over there. Okay, so if we assume that it's over here and we don't know where it is, we're going to set a distance over here of L0. We don't know what this is, but we're just going to call this distance to that charge L0. Okay, so we've got charge 1 and charge 2, and then our new charge over here, which we don't know what it is going to be charge number 3. Okay, so the equation of force between these two is going to equal, so we'll call this F13, okay? This has to equal K times Q3 times Q1 divided by L0 squared. Okay? And then we've got to take into, so that's the force between these two particles right here. Okay? That's the force right there. But we have these other two particles over here, so between 3 and 2, okay? So this is going to be F23 is going to equal K times Q3 times Q2. Okay, now the distance here between charge number 2 right here and charge number 3 is going to be L plus L0. So this is as I like to call it, a math trick to make solving the problem easier, but nonetheless it is important. Okay, so now the final step, we have to say, what is the condition of equilibrium on this third charge? And that equilibrium means that the net force is going to be 0 on that charge. Okay, so what we can do is we can say that my net charge, so F net, is going to be the sum of all my charges, so Fn. So I'm going to sum all my charges together here. So this will be F13 plus F23, and my net force is going to be equal to 0. Okay, so these are my conditions here. So then I'm going to say, okay, I will have K times Q3 times Q1 over L0 squared plus K times Q3 times Q2 over L plus L0. That's a squared right there. Okay, so in my picture here, one force is going to be pulling to the right and one force is going to be pulling to the left. We don't know what Q3 is, so we are going to kind of ignore the charges for now, and we're going to say the absolute value of Q1 times Q3 divided by L0 squared minus, we're going to take the difference here because we want the sum to equal 0. We know that the forces are going to be in opposite direction because if I go back up here, one force is going to be pulling and the other one is going to be pushing, and so they're going to be in opposite directions. So we're going to have K times Q1 Q3 times Q2 divided by L0 plus L, and this should be squared right there. Okay, and then I'm going to set this whole thing equal to 0. Okay, because I don't know what the sign of Q3 is in either of these. Okay, but I know that the forces are going to be in opposite directions, so I'm going to add these absolute value signs, just find the difference and say this thing has to equal 0. Okay, so what I get is, now my equation becomes K times Q1 times Q3 over LZ squared minus K times Q3 Q2 over L0 plus L squared equals 0. Alright, well this is good because right away I can see that Q3s are going to cancel, my K's are going to cancel, and now I just end up with this part here. So I will get Q1 over L0 squared is equal to Q2 over L0 plus L squared. So I am going to end up with, starting on a new piece of paper, L0 plus L squared divided by L0 squared is going to equal Q2 divided by Q1. Okay, so I'm going to take the square root of both sides. So this will be L0 plus L divided by L0. Then I'm going to take the square root of Q2 over... Oh, that should be a Q1 right there. Q1. Okay. Okay. So, Q2, that's a Q2, is going to equal minus 3.02 microcoulombs. That's what we said way back here at the beginning. And Q1 is going to equal 0.96 microcoulombs. Alright, so I'm going to put that in here. And then L, in my problem, what do we say L was? Look, here we go. There's our problem. So they are separated by 0.93 centimeters. 0.93 centimeters. So now I will get L0 plus L divided by L0 is going to equal Q2. So that's going to be minus 3.02. And I'm just taking the absolute value of this. So I don't have a negative sign there. That should be positive. My negative sign is not there. This is microcoulombs divided by 0.96 microcoulombs. Okay, so microcoulombs cancel, and I can get my answer in centimeters. I don't actually need to convert into meters on this one. Mathematica gives me 1.77365 for the square root of 3.02 divided by 0.96. And I'm going to keep my significant digits in there for now. And then later at the end of the problem, I can put in the right significant digits. Alright, so now I get L0 over L0 plus L over L0 equals 1.77365. This just cancels and becomes 1. So now I will get L over L0 equals 1.77365 minus 1. I will multiply by L0 on both sides. These cancel. And so now I can solve for L0. I will have L0 divide both sides by 1.77365 minus 1. So my L0 will stay over here. And now I will get L divided by 1.77365 minus 1. So now we can enter this into Mathematica. And we have L is equal to, that's L0. L0 is equal to L divided by 1.77365 minus 1. And that's going to be the equation. And then I'm just going to use the top part here. Alright, this part is 9.3, which will give me 12 centimeters. This will be L0 equals 12.0209 centimeters, but that's way too many digits, so we're just going to say 12 centimeters. These really are not meaningful. Way more significant digits than we had in the original problem. So this will just be L0. Alright, so when we put it all together, we end up with 12 centimeters. Now we have the distance to the charge, and it is on the left side, and the y y is going to equal 0. So this will be y equals 0, and it's going to be on the left side. So this will be minus 12 centimeters. Let's draw our final picture. Okay, here is our negative charge, 0.96 centimeters. Then over here, put that over there, we have a positive charge of 3.02. So, oh, my snout is too big in this picture. Then our other charge, and I drew them kind of at an angle, is going to be over here, much farther away. Slide my document cam. So this will be about 12 centimeters over here. And so if our x-axis is, well, it's kind of tilted here, but that means we're going to go negative this way. And so the x-coordinate is going to be minus 12 centimeters, and y is going to equal 0. There you have it. Problem number 11. Thanks. No, wait. What problem is it? Problem number 13. Thanks for watching. Have a good
Thank you. Like and subscribe down below.